Hello everyone and welcome to another video on our own devices. I'm Jean Messier, and so far on this channel I've covered a wide variety of radiation detection instruments, from ion chambers to spinthariscopes, quartz fiber electrometers, scintillation counters, and even cloud chambers. But the one type that I haven't covered yet is the most famous of all, the Geiger counter. So that's what we're going to be looking at today. Now, this particular example I found at a flea market, and immediately something seemed off about it because while the construction is overall very good, there isn't any sort of data plate or other indication of the manufacturer. And when I opened the unit up, holy radio batteries, Batman. As you can see, this is just crammed full of 7 batteries of 5 different types, and this, along with the crude construction of the internal electronics, indicates that this was a homemade unit, possibly dating from the 50s or 60s. And indeed, this was a very common homebrew project at the time. No guesses as to why. And since this is basically the simplest Geiger counter you can have, this is a great example to show you how these actually work. So let's dive right in. So the inventor and namesake of the Geiger counter was German physicist Hans Geiger, who was born in 1882 and obtained his PhD in physics from the University of Erlangen in 1906, his thesis being on electric discharges through gases. Now, that same year, he moved to the University of Manchester to work under the physicist Arthur Schuster, but when Schuster retired the following year, Geiger instead went to work for the legendary Ernest Rutherford. Now, at the time, Rutherford was studying the properties of alpha particles, which are known to be emitted by certain radioactive elements such as uranium and radium. And Rutherford had a theory that alpha particles were actually helium ions with a double positive charge. To confirm this, he needed to determine the charge to mass ratio of the alpha particle. So in order to do this, he assigned Geiger and undergraduate student Ernest Marsden conduct an experiment in which they would count the number of alpha particles emitted by a sample of radium within a certain span of time, and then measure the charge deposited by said alpha particles during that period, allowing them to determine the charge of an individual alpha particle. Now, at the time, the only way to detect an individual alpha particle was using a phosphorescent zinc sulfide screen, like in a spinthariscope, which I've covered in a previous video, link in the description. And unfortunately, this was a very tedious and often inaccurate process, requiring experimenters to spend hours in the pitch darkness, squinting through a microscope to catch very brief and often very faint flashes of light. So Geiger and Rutherford set out to create an instrument that could automatically detect and count these alpha particles. And their design was based on the work of John Townsend, who back in 1902 determined that not only can an alpha particle ionize molecules of air, but if this occurs in an electric field, ion pair produced, the free electron and then the ionized gas molecule, will travel in opposite directions. And if this field is strong enough, the electron will be accelerated to such an energy that it will start colliding with and ionizing further gas molecules, creating more and more electrons, a cascade or multiplication effect known as a Townsend Avalanche. So Geiger and Rutherford's instrument consisted of a glass tube filled with low-pressure air with 2 electrodes across which they passed a high voltage. And the idea was that as an alpha particle entered the detection tube, it would start ionizing air molecules along its path. The electric field would then separate the ion pairs, accelerate the electrons towards the anode, which would then trigger a number of Townsend discharges, such that a single alpha particle could produce an electric pulse large enough to be easily measured and counted by very simple circuitry. Now, while the theory was valid, in practice, this detector proved very unreliable, with alpha particles of the same energy yielding very different readings. And Geiger and Rutherford realized this was because the alpha particles were being deflected by large degrees by the gas molecules, meaning that each alpha particle would ionize a different number of molecules before exiting the tube, thus producing different readings. And this was an unexpected result because at the time, the leading model of the atom was J.J. Thomson's so-called plum pudding model, where electrons were embedded in a cloud of positive charge like plums or raisins in a pudding. And according to this model, atoms could not deflect alpha particles by the degree that Rutherford and Geiger were seeing. So the team embarked on a series of experiments to study the alpha particle scattering properties of various materials. And this culminated in the now legendary 1913 experiment where Geiger and Marsden fired alpha particles from radium at a thin piece of gold foil and used a curved zinc sulfide screen to measure how far they were deflected. And to their astonishment, once in a while, an alpha particle would be deflected at an extreme angle, sometimes beyond 90 degrees, coming back at the alpha particle source. And this led Rutherford to famously declare that it was as if he had fired a 15-inch shell at a piece of tissue paper and it came back right at you. And this led to the discovery, the revelation, that most of an atom is actually composed of empty space with most of its mass concentrated in a small, dense nucleus. And this was the birth of nuclear physics as we now know it. Now, it wouldn't be for another 20 years, in 1928, that Geiger, along with his graduate student Walter Müller, took his original 1908 detector and improved it to produce what is now known as a Geiger-Müller tube. And this lies at the heart of every Geiger counter. So let's take this one apart and let me show you how it works. So as you can see, this is an EW3H Geiger-Müller or GM tube manufactured by Century Electronics. Unfortunately, this particular example is broken. The electrodes on the inside have broken away from the universal vacuum tube base, but I can still show you some of the major components and how this works. So a GM tube consists of a metal or glass tube filled with a low pressure mixture of gases, typically at around 0.1 atmospheres. This mixture is mainly composed of a noble gas, such as helium, neon, argon, krypton, or xenon. Most commonly used is neon, though heavier gases like xenon and krypton are used to detect gamma rays. There's also a small amount, typically 1 to 10%, of either an organic vapor like butane, ethanol, or methane, or a halogen, typically chlorine or bromine, which acts as a quenching gas, though more on that in a little bit. Now, there are two electrodes in here, a cylindrical cathode and a wire anode running down the central axis. And this particular tube is what's known as an end window type, and this is for detecting both alpha particles and beta particles. Now, alpha particles don't have very much penetrating power. In fact, they can be blocked by a piece of paper, human skin, or even just a few centimeters of air. And so to allow them into the tube while maintaining the gas seal on the tube itself, you need to include a window made of a very thin and low density material. And the classic material for this is mica, which we see in this case. However, since this also easily allows in the more penetrating beta particles, this type of tube can't discriminate between the two types of radiation. Though if you hold the tube more than a few centimeters away from a radioactive source and you're still detecting radiation, those are probably beta particles or gamma rays because the alpha particles will have been blocked by the intervening air. There are also windowless GM tubes completely encased in a stainless steel envelope, and these are used for detecting high-energy beta particles as well as X-rays and gamma rays. Now, these work in one of two ways. For detecting high-energy beta particles and low-energy X and gamma rays, the envelope is thick enough to exclude alpha particles, but thin enough to allow in the desired radiation, which will then interact with the detection gases and trigger an ionization event. However, higher energy X-rays and gamma rays don't interact very strongly with most detection gases. And so these tubes will have a thicker wall so that the incident radiation will interact with the wall to produce a shower of electrons by the photoelectric effect. And these electrons will then interact with the detection gases inside the tube. Indeed, you can even detect neutrons with a GM tube by coating the exterior with a boron compound or cadmium, or filling the interior with boron trifluoride or helium-3. And so neutrons will interact with the boron to produce alpha particles, with the cadmium to produce gamma rays, or with the helium-3 to produce tritium and protons, which will then interact with the detector gas as per usual. And indeed, this is very similar to how English physicist James Chadwick originally discovered the neutron in 1932. He fired alpha particles from a polonium source at a piece of beryllium, which knocked free neutrons, which were then directed into a block of paraffin wax, where they knocked free protons, which then traveled into an ion chamber where they could be detected. But whatever the specific design details, all GM tubes work pretty much the same. So just as in Geiger's original 1908 instrument, When a particle passes through the tube, it ionizes gas molecules along its path, producing ion pairs. Now, the free electrons are drawn towards the anode at the center, while the positively charged gas ions are drawn towards the cathode around the edge. Now, the electrons are accelerated to such a degree that as they approach the anode, they have so much energy that they can start colliding with and ionizing gas molecules, producing more and more electrons via the Townsend Avalanche effect. But if the number of Townsend discharges only equaled the number of original ionization events, then the electron multiplication factor would only be on the order of 10 to the 6 to 10 to the 8. However, those Townsend discharges also release ultraviolet photons, which, being unaffected by the electric field, travel laterally along the anode wire and trigger further ionization events and further Townsend discharges. And this increases the electron multiplication factor by 10 to 100 times, creating a more powerful electric pulse that can be more easily measured using fairly simple circuitry. But before we further explore the intricacies of GM tube design and operation, let's have a look at the rest of this Geiger counter. Right, so as I said, this is about as simple as it gets. We have our readout dial here, calibrated in counts per second, aka becquerels, named after Henri Becquerel, the discoverer of radioactivity. You've probably also heard of a unit called a curie. That is 3.7 times 10 to the 10 becquerels and is equivalent to the radiation emanation of 1 gram of pure radium. We also have a jack for our probe with our Geiger-Müller tube in it, a 1/4-inch jack for a set of headphones, as well as a selector switch with 4 positions: off, 100 times, 10 times, and 1 times amplification. And that's pretty much it. So let's open up the inside and see what we can find. So as I mentioned at the beginning, this is absolutely jam-packed with batteries, which make up most of the weight and volume of the unit. Specifically, we have 2 300 volt, 1 90 volt, 2 45 volt, and 1 1.5 volt radio batteries, and 1 30 volt hearing aid battery. And these are connected in 4 different blocks. One supplies high voltage to the Geiger-Müller tube, while the others supply the A, B, and C, that is filament, grid, and plate voltage, to the vacuum tubes in the amplifier. Now, most Geiger counters include some sort of inverter circuit to increase the battery voltage to that required by the GM tube, allowing the use of fewer batteries and cutting down on weight and bulk. This one, however, brute forces things by supplying the high voltage directly from the batteries. Interestingly, while the GM tube in this example is rated for 640 volts, the batteries are connected to supply it with 690 volts. This is likely to maximize the strength of the pulses coming from the tube, though it also probably pushes the tube to the edge of its operating envelope. If the voltage were any higher, the tube would likely start discharging continuously after detecting a single particle. Right, so the detection circuit itself is not the absolute simplest you can build, but it is still fairly minimalist. Unfortunately, however, the build quality on this is rather crude. The circuit does not match any period instructions I've been able to find, and it's very possible that this unit is incomplete and missing components. All this means that neither I nor my assistant, who is far better versed in vacuum tube electronics than I am, have been able to fully parse out how this works. Now, in simple Geiger counter circuits, integration of the pulses from the GM tube into counts per second is done using a capacitor, which converts the pulses into a voltage that can be read using a voltmeter. The capacitance, as well as the internal resistance of the voltmeter, determines the time constant of the integrator. That time constant can be altered by swapping in different values of capacitors, thus allowing different ranges of count rates to be displayed. Typically, the charging of the capacitor is accomplished using a neon lamp, which doubles as a handy indicator for each detection pulse. However, the absence of such a lamp and the presence of the 2 vacuum tubes indicates this circuit is a bit more sophisticated. And this appears to be a monostable multi-vibrator circuit, which is a type of relaxation oscillator that, when triggered by an input pulse, goes through a timing cycle and outputs a longer square pulse. The width of this pulse is determined by the value of a timing capacitor, and so by swapping in different capacitors using the selector switch, you can vary the width of the output pulse, and thus the range of count rates that can be detected. Other than that, however, the only other component whose function I can point out is this disc capacitor, which couples the output of the GM tube to the headphones to prevent 690 volts from being conducted directly to the operator's head. But again, much of this is a guess, so if anybody watching has built a Geiger counter like this and knows exactly how the circuitry is supposed to work, please let me know. Now, getting back to the design and operation of Geiger-Müller tubes, this is where things start to get a little bit complicated, because ideally we want a radiation detector to produce a single pulse per detection event and to have as short a reset or dead time as possible. It's no good having a radiation detector that takes forever to reset, meaning it can be overwhelmed by large count rates, or that detects a single particle and then starts discharging continuously, rendering it useless. Now, the mechanism which halts each of the pulses has to do with the other half of the ion pairs produced, that is, the positively charged gas ions. See, having a greater mass, these migrate towards the cathode more slowly than the free electrons do towards the anode. This produces an electric field that opposes the main electric field between the two electrodes and prevents the electrons from accelerating fast enough to trigger more Townsend avalanches. And this brings each pulse to a halt. And for a given GM tube design, the pulse cuts off after a fixed number of Townsend avalanches, meaning the intensity of the detection pulse is independent of the radiation that triggered it. This means that Geiger-Müller tubes can't discriminate between different types of radiation, nor can they give you any spectral information, that is, information about the energy of the radiation being detected. To do that, you need to use a scintillation counter, which I've covered in a previous video, link in the description, or something called a proportional counter, which we'll get to in just a second. However, this effect of the migrating positive ions isn't enough to prevent spurious discharges. And this is because as those ions reach the cathode and gain new electrons, becoming neutral again, they also jump to a higher energy level, and they release that excess energy by emitting ultraviolet photons that trigger further ionization events and Townsend discharges. This is why, in addition to the regular detection gas, GM tubes also include a small amount of what's known as a quenching gas. And how this works is that once the detector gas ions become neutral, they collide with the quenching gas molecules and transfer over some of their excess energy. Unlike the detector gas molecules, the quenching gas molecules release this excess energy not by releasing photons, but rather by splitting into smaller atoms or molecules. This prevents spurious discharges and reduces the tube's dead time. Now, as I mentioned before, in older tubes, the quenching gas was typically an organic vapor, such as butane, methane, or ethanol. But in 1947, physicist Sidney Leibson introduced the use of halogens, chlorine and bromine. Now, halogen quenchers have two main advantages over organic quenchers. Number one, they allow GM tubes to run at much lower voltages, between 400 and 900 volts, as opposed to over 1200 volts for older tubes. And second, when organic quenchers break apart to release excess energy, they cannot recombine again, meaning that eventually they will be used up and the tube will become useless. Also, the products of these molecular decays will eventually gum up the interior of the tube. Halogens, on the other hand, can recombine over time, and thus halogen quench tubes have a much longer service life than older organic quench tubes. Now, interestingly, quenching can also be accomplished electronically as well as chemically. In so-called externally quenched Geiger counters, the power supply to the GM tube is very briefly cut off for just a fraction of a second immediately after detecting a particle, allowing the pulse to die out before the power is restored, allowing the tube to detect further pulses. However, even with the best external quenching available, Geiger counters are limited to detecting count rates of about 10 to the fifth counts per second. Any more, and the dead time, the reset time for the tube, is so long that the tube can't detect anymore. It gets overwhelmed. And to detect these higher count rates, you typically need an ion chamber, which we've covered in several videos before. And this ability to handle these high count rates is why ion chambers are primarily used in civil defense and military gamma survey meters. Now, another shortcoming of Geiger counters that I mentioned before is the inability of the Geiger-Müller tube to discriminate between different types of radiation or to give you any spectral information, that is, information on the energy of the particles being detected. Now, in order to do this, again, you can use a scintillation counter or something called a proportional counter. Now, the proportional counter was invented in 1948 by one Samuel Curran, a Scottish physicist who you may remember from a previous video, also invented the scintillation counter in 1944. Very busy guy. Now, the proportional counter is almost identical to a regular Geiger counter, only it uses a specific combination of tube geometry, gas composition and pressure, and applied voltage to minimize the production of additional Townsend discharges by ultraviolet photons. This means that the number of Townsend avalanches is directly proportional to the number of original ionization events, and thus the energy of the particle being detected. Now, interestingly, ion chambers, proportional counters, and Geiger counters lie along a continuous spectrum depending on the applied voltage. So, at low voltages, the detector will act as an ion chamber where the electric field is strong enough to separate the ion pairs, but not enough to trigger Townsend discharges, producing a continuous current opposed to discrete pulses. At intermediate voltages, the detector will act as a proportional counter, while at higher voltages, you get UV-triggered propagation of Townsend avalanches along the anode, causing the detector to act like a Geiger counter. And finally, beyond the Geiger region, the voltage is so high that the detector will start discharging continuously after detecting only a single particle. And that, dear viewers, is a brief overview of the history, design, and function of the Geiger counter, perhaps the world's most famous radiation detection instrument. This also means that I've pretty much covered all the major radiation detection instruments there are. Though if I've missed any major ones, or if there are some really obscure ones that you would think would be interesting to cover on this channel, please let me know in the comments. Until then, I'll see you next time on another video where we'll look at yet more radiation detection equipment, maybe, and other fascinating devices just like this one. Until then, I'm Jean Messier from Our Own Devices. Have a great day.